All right, when you're using programming to work with languages, it's natural that you're going to be working with a lot of strings. So let's take a closer look at how Python and the computers in general, handle strings kind of behind the scenes. So ASCII values is how text is represented in computers. So it's analogous to how binary represents numbers. And of course, eventually it's all represented as numbers for the computer, binary numbers. In fact, ASCII uses the binary numbers and gives every character in a spelling system, orthography, a unique individual numerical code. And that's how those strings and the elements in a string are represented. And as we know, or we could conclude from what we know about lowercase and uppercase, these characters are separate. They're different codes. The codes for ASCII go from 0 to 127. Now think about, why 127? Well, you probably know that binary numbers in computers are organized into 8 bits, right? So each place is a bit, and we just talk about 8 bits or a byte, right? So as we know from binary numbers, if you have 1 in 8 places, so 8 bits with 1 in them, that's 2 to the 7th, which is 128. So you have the potential to have 128 numbers. And if you start at 0, then the 128th number is 127. So the ASCII characters are represented with codes that can be fit into and represented by 8 bits. Here's the ASCII table. So this shows the decimal, the hexadecimal representation and the character that those numbers represent. And if we see here, we have all of the Latin characters, upper and lowercase, plus pretty much all the punctuation you would need in a Latin writing system, plus some other things that we're familiar with, such as, carriage return or line feed, things that are giving us new lines, backspace, and other things that we've worked with when we did string and string formatting. So our first column here is actually the control characters, such as the ones I was just mentioning, that control how the string is dealt with in the computer. The second column is symbols and numbers, so punctuation and numbers, the digits 0 through 9. The third column is all the uppercase characters, which note they come before the lowercase characters that are in the fourth column, plus some punctuation as well, mixed in there. And if you'll notice, the chart here, the table, is arranged in such a way so that the uppercase letter and its corresponding lowercase letter are next to each other in the columns. So you can add, so the number here, 32, so 97, so this is the number for lowercase b, 97. 65 is the number for uppercase. You can add 32 to the uppercase and get to the lowercase, and that's true for all of the alphabet here. If you add 32 to the uppercase value, you'll get the corresponding lowercase. So since characters, ASCII characters, are actually represented numerically, when we compare strings together, we're actually looking at the values, the numeric values of those ASCII characters, which can lead to some weird results. For example, if you compare cat to dog with the less than operator, you'll find that actually cat is less than dog. That's true. But if dog has a capital D at the beginning, actually it's not true. And you can go back to the ASCII table and do the math and figure out what's going on here. So you get some weird results because you're actually comparing the numeric values that are representing the ASCII characters. Capital dog, all capital letters, is actually less than lowercase dog, right? Well, that makes sense, right? Because the capital letters come first, they're lower numbers than the uppercase numbers. It gets even more complex when you start adding numbers and symbols into your strings. So 2 as the string, the digit 2 as a string is less than the word 1. So 2 is actually less than 1. I bet you didn't know that. Good as a question is not less, however, than good as an exclamation. I don't know if that means one is better than the other to ask a question to make an exclamation, but there you have it. UK without the periods between is not less than UK with the periods in between. So here's some hints. So you're working with comparing strings, you're going to run into these weird results. So here's some hints of how to avoid some of these issues when you're comparing strings. Always use dot lower or dot upper, but dot lower I would recommend for comparing strings. That way you make sure that you're going to have all your letters are going to be the same value. Pay attention to your symbols, right? So this is something that came up in our lab when we worked with the file with all those names in there. When you were looking for the string Darth, if you were trying to see if Darth was in there, and for those who had left off the new line symbol in that string, it wasn't working. Unless, of course, you first stripped off that new line character. So when you're comparing strings, pay attention to the symbols that might be attached to them, the Python symbols that you might not see in the text file. Spaces, hyphens, punctuation, new line characters, tab characters, etc. And either remove them or just remember that they're there and allow for that when you compare. Another interesting thing we can do to see how this whole system works is we can actually convert between the ASCII characters and their numeric values. And there's two functions that we do that, ord and tra. So ord kind of stands for ordinal. It's a function that takes in a single character and returns its ASCII numeric value as an ordinal number. The tra, or the character function, takes an integer, so a numeric value, and returns its corresponding ASCII character. So with ord, you go from the character, and you can see the underlying numeric value, and the character function does the opposite. So we can do character function on 65 and find out that 65 is the value of capital A as a string. Here we show we're adding that 32 to the number for capital A, and we're going to get lowercase a. So nice convenient operation there. If you have a symbol, such as a question mark, you want to find out what its numeric value is, you run the ord function, and it's 63. So if you try to do a comparison between the question mark and capital A, question mark would come out as less than capital A. Kind of strange. The ordinal for lowercase d is 100. And of course, you get the uppercase d by subtracting 32 from that. And then the ordinal for E, I bet you could guess, since it's right after d, is 101. So the ASCII table is in alphabetical order. Now, ASCII, as you may have noticed, only covers the Latin alphabet. So it's only going to work for languages that use the Latin alphabet, such as English. And that's certainly not all. And if you just limit it to English characters in the Latin alphabet, it's probably not even most languages in the world. So to solve that issue, to allow computers to represent, well, hopefully all writing systems, the Unicode project extended the original ASCII characters beyond the 8 bits so that we could have a very large range of characters. And we can do more and type in more orthographies than just the Latin one. The Unicorn project has a motto. The Unicode will provide a unique number for every character, no matter what the platform of the operating system, no matter what the program or programming language, and no matter what the language. So hence UNA for universal, and the code, the universal code for all language writing systems. And Python 3, which is the version we're learning in this class, fully supports Unicode, so that special symbols from other writing systems will behave the same as Latin symbols. This is different from Python 2 if you ever use it or have used it in the past. So you can go on to unicode-table.com and you can see the whole schema for representing all of these characters. And here's the corresponding, or part of the corresponding part for the original ASCII characters. So here's our basic Latin characters with some punctuation. You can see the range of the numeric codes here in hexadecimal, and the number, the alphabet, and then some examples of the languages that use them and where they're located in the world. So that's our basic Latin. Unicode also has Cyrillic, which is the writing system, the alphabet used in Russian, Ukrainian, Bulgarian, and actually many other indigenous languages in the former Soviet Union also use Cyrillic. So you'll see some symbols here that aren't used in the kind of original Cyrillic, if you will, of Russian, such as this, which is used in Ukrainian. You wouldn't have any reason to know this unless you knew Cyrillic, but it actually includes symbols for the Old Slavonic language, which now is pretty much just used in icons in the Russian Orthodox Church. So it covers quite a bit. And then down here we have some symbols that are used in indigenous languages of the former Soviet Union. So it covers all of those languages. It also covers indigenous languages in North America. So this part of the table right here is for the Cree languages, which is spoken, it's actually a group of languages, kind of a dialect chain that's across most of Canada. And they actually have what's called a, I'm going to pronounce it wrong. I always put the emphasis on the right word, but well, all right, we won't do that. That's what it is. There, it's written for you. You can look up the pronunciation. You'd think a linguist would be able to do better than me. But what that is, which is interesting, is that the symbols actually represent syllables, not letters. So this is the Cree writing system. Unicode covers it. And in case you want to do that next college essay in Egyptian's hieroglyphics, there you are. You can do that on the computer. You can type in the hieroglyphics, just like the ancient Egyptians did. Who would have known? So it's pretty cool. It's very extensive. Covers all the languages. Oh, even alchemy symbols. So if you're planning on doing some work to turn linguistic data into gold, you're all set here. It can be represented in the computer, and Python 3 will handle it just fine. And again, just like with ASCII characters, you can use the same functions, the character and the ordinate functions, and you can take an integer value, put it in the character. In this case, it's representing a symbol. It's not, so you can get some different results here. It's not giving the symbol, it's giving the underlying hexadecimal number for that code in this particular environment. You can take another number. So in this case, it's going to, has no problem. It's going to display the Cyrillic letter for Y. And you can take symbols and use the ordinate function and get their numeric values in decimal. And even here we have the alchemic symbol for vinegar, and we can get a much larger number that is its numeric value. So these functions work with ASCII, the original ASCII characters, and with all Unicode symbols as well. Okay, so I said that Python 3 handles Unicode just fine. It doesn't mean that everything's going to be encoded in Unicode, even though it's a universal, or it's supposed to be universal. By default, Python 3 opens files with Unicode, and specifically what's called UTF-8 encoding. However, you can assume that. So sometimes you have to put in your own encoding. To avoid encoding errors, you have to specify the file's encoding. And sometimes I've found, even with Python 3, that I have to specify the UTF-8 encoding. So to do that, here's a new optional argument for the open file when you're opening files, either to read them as a top line or to write them, is you have this encoding equals, and then you would put in UTF-8 to indicate the Unicode, kind of the default Unicode encoding. And of course, you can leave off the optional R for reading, or include it, or include the W, and then the encoding would come after those.